Hello.
Hello. Good morning,
And there's
everyone.
Nathan and Mohammed. Hey, bud, how are you?
I'm good, sir. How are you?
I'm fine. trying to pin myself here somehow. So we have, I need a bigger picture than that. That's not. Seem to be having trouble here. Maybe I'm supposed to click on Zoom again. I don't know.
Are you trying to pin yourself?
Yeah, obviously I don't know how.
I think you need to have your camera on, because right now it's just showing a picture.
Oh,
And
the camera's not on, huh? That's not good. Well, let me try again here. I see Alex is with me. I don't know what I'm doing wrong here, guys. Just bear with me. We'll get this figured out. Nathan's here.
Is your start video icon the lower left-hand corner? Is it on?
Start video on the left. I don't see a start video in the left hand. Well, let me call my IT person here. There's Bryce.
Hello.
Hello.
How are you doing today?
Oh, terrific. I'm trying to, hey, I'm having a little trouble getting this second meeting started here. Yeah, I did.
We can see it now.
Hey, the camera came on, but I'm not seeing anything. Wait a minute. Hey, I think I'm okay now. I think I'm okay now. All right, ta-ta. That was my IT person. My youngest daughter, she's 30. My oldest daughter's, well, she was born in 69, so that means she's 51, right? Yeah. She's 51. Makes you feel old when you have a 51-year-old daughter. Okay, well, welcome everyone to Thermodynamics. And let me see who I've got here. Oh, a good crowd. Alex, Andres, Braxton, Brian. Oops. Somebody asked, Nicholas asked, did the professor go over quality on Tuesday? And the answer was no, he did not. And that's the first thing we're going to go over. So you guys are on the ball. You're anticipating what I'm going to do here. Good
Also,
for you.
Mr. Griffin, can you go over the problem 2-36?
Yeah, I'd love to. Yeah. We have Tyler, Reagan, Nicholas, Nathan, Daniel, Mohammed. Got a good group. Now, Mohammed wants me to go over 2-36. I want to talk about quality, but let's see what this 2-36 is, and then 2-36. Constant pressure piston has a water. Yeah, now this problem talks about quality, so let me explain quality, and then I can help Mohammed with 236. The topic for today is PV diagrams, and I told you that they are the most important thing you need to master. You'll do okay in this class if you can master those. But there's an equation for dealing with quality, and it goes like this. But I want to explain this equation to you. I guess you could call that the quality equation, where that value of X is something called quality. And what it is it's the percentage vapor you have. So for instance, if you have 100% quality, then you're all vapor. If you have 0% quality, 0% quality, then you're all liquid. No vapor at all, it's all liquid. Let's say you were 50% quality. Or you could write X is equal to 0.50. That's the same thing as saying 50% quality. You know what that means? That means you're half vapor and half liquid. So now we know what quality is. Now we don't really know about this equation yet, but I'm going to explain it right now. This, of course, is our friend, the specific volume. We all know what specific volume is. It's the volume over your mass. Now they got a little F there. What that is the specific volume if you have all liquid. And then they got a little, here, let me write this. They have a little VG, and what that is the specific volume if you're all vapor. Now what this VFG is they took the specific volume if you're all vapor and they subtracted the specific volume if you're all liquid, and they call it F, the specific volume FG. It's the difference between the specific volumes of all vapor and all liquid. Okay, now let me show you where this equation came from. This will make perfect sense to you all, hopefully. Suppose you had a container. It could be a piston cylinder deal. Here's a piston cylinder, and you got some liquid down in the bottom. Here, let me get my blue. I've got some blue here, and there's some liquid down there in the bottom. See, I'll color it blue. There you go. But see, the rest of it is vapor. It could be water. It could be steam, okay? It could be liquid water and a bunch of water molecules of steam there. And here's my plan. The total volume in your piston cylinder should equal the volume of your liquid plus the volume of the vapor. That should make sense to all of us. Doesn't that make good sense? The total volume would be, if you took the volume of your liquid, added the volume of the vapor, you would get the total volume. Okay. Now you could write that total volume as the mass, the total mass that you have, times the total specific volume. See, specific volume, what that is total volume divided by the mass. Can you see that the total volume would equal the mass times the specific volume, total specific volume? This is a definition here. Okay, and this here would be the mass of your liquid times the specific volume of your liquid. This would be the mass of your vapor times the specific volume of your vapor. So far, so good if you understand all that. Now we're going to do a little algebra trick. We're going to divide through by the total mass. That's legal. In algebra, you can divide through by a number everywhere in your equation, and it's still okay. Now, you guys see this mass of the vapor over your total mass? That is the quality. That's what quality is. Quality is the mass of the vapor over the total mass. Didn't I tell you that quality was the percentage vapor that you have? We see if you have 100% quality, then the mass of your vapor would equal the total mass. If you have 0% quality, you wouldn't have any vapor at all. It would be all liquid. Now this right here is a little bit subtle, but see, this is going to equal to x, and this is going to equal to 1 minus x. I want you to think about this. Suppose you had a quality of, say, 30%. If you had 30% quality, that, you know what that means? That's 30% vapor, huh? If you have 30% vapor, then you have 70% liquid. See, if you have 30% vapor, if that's the quality, then you have 70% liquid. In other words, you have 1 minus x for your liquid. Because see, the quality, if it was 0.7, or no, if it's 0.3, there we go, you get 0.7. Hope I didn't lose you on that, but we're almost done, and we almost have our equation. Do I have room here? Yeah, I barely do. Okay, look. That cancels out, and you have the total specific volume. Make that darker so you guys can read this. The total specific volume is 1 minus x times the specific volume of the liquid, which they call VF. That's their little secret symbol for it. Plus x times VG. VG is their little secret symbol for the specific volume of your vapor. Well, it's just one algebra step to get from here back up to here. I bet you can make it. Because see, this is going to equal VF plus x times VG minus VF. Can you get from here to here? Can you make it? It's just algebra. Now this right here is called VFG. They've subtracted it for us. Isn't that nice? And so now we've shown you this valuable equation for quality. We're going to be using that. So put that in your notes. We need that. We're talking about inside the vapor dome. See, inside the vapor dome, you have what they call a saturated mixture of liquid and vapor, and you need this equation. Now we're going to do Mohammed's problem. He wanted to do, I think it was 236. Mohammed, it was at 236? Earth calling Mohammed.
Yes, it was 236.
Say that again, please.
It was 236.
Yeah, okay, let's do that. Here we go. Do I have any? Go ahead.
It's on page 8.
I don't hear anything. Do I have any questions on that? Any questions? Okay. Well, let's erase that, and we're going to do 236.
You have him.
Okay. All right, we're going to do 236 now. Now, what is the key to success in this class? Let me ask somebody here. Since Mohammed asked me this question, Mohammed, what is the key to success in this class? What's the most important thing you got to know how to do in this class? Go ahead, Mohammed.
To keep learning the PV diagrams in this class.
The key. Say again, please.
Keep learning on those PV diagrams. We need to
That's
master
it.
those.
It's the PV diagram. The PV diagram is the secret to success in this class, and Mohammed knows that. That's good. Okay. Well, let me find this problem. It says constant pressure piston cylinder has water at 1,000, quality of 25. I'm going to do the device sketch first. This is called the device sketch. And I'm going to do state 1. It's going to look like this. We know we got some liquid and some vapor. In fact, what is it? A quality of 25%. 25% vapor by mass and 75% liquid by mass. So it's not by volume, but by mass. So we do have some liquid in there. And we're going to lower the temperature. We're going to keep the pressure constant. I'm kind of confused. I'm having trouble with my device sketch, so I'm going to go to a PV diagram. That'll help me. Now we know this is water. And we know we have a vapor dome like that. And we know we have 1,000 kilopascals. Well, this up here is way up here at 22,000. So 1,000 kilopascals is down here pretty low. We'll put it here. I'll just fake it there. 1,000 kilopascals. And we know we're inside the vapor dome. Here's your isobar. We know we're inside here with a quality of 25% at 1,000 kilopascals. Let's go ahead and get the specific volume. Well, help me find 1,000 kilopascals. If you just tuned in, we're doing a problem for Mohammed. He wanted me to work on 236 for him, which is fine with me. And I've got to find 1,000 kilopascals.
Should be A24, page A24.
No, I need page A30. This is table B.1.2. And the little v there is 0.001127. The quality is 0.25, and the VFG is 0.19322. Did I get that right? No, 19332. Now, before I go on, can everyone find those numbers on table B.1.2? It's actually my appendix on page 30.
Yes.
I heard a yes. How about another yes?
Yes, I have a question though.
Okay, go ahead.
This table says saturated water pressure entry, and I notice that it's got a VFG. The saturated water pressure entry, what does that have to do with the quality? I did not use the right table for this problem, and I'm curious to know how I know to use this table.
Which table tell me your name and which table did you use?
Nathan, I used table B11.
Okay, you could use that table, but you'd have to interpolate because they didn't give you the temperature, Nathan. They gave you the pressure. They said the pressure is 1,000.
Okay, and that's what
it's
I
just
did.
A lot easier
Okay,
to use the table.
Yes, I'm sorry, I'm talking over you. That is what I did, but it only changed the temperature by 0.1 degrees.
Yeah, I mean,
but
you can do that. You're fine. It's just that it's easier if they give you the pressure to go to the table that has the pressure. Okay? Just easier. Okay. Let's go ahead and get this V. Here we go. I'm going to get the specific volume now, and I want you guys to do it. 0.001127 plus 0.25 times 0.19332. Ta-da! I've got my answer, I think. Uh-oh, something bad happened. Let me do it again. 0.001127 plus 0.25 times 0.19322. No, it's 332. 332. Okay, I've got the specific volume is 0.0494 blah 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 cubic meters per kilogram. Now while we're at it, let's get the temperature. Now they said the temperature is 179.91. I like my temperature in red. Let me get my red pencil out here. 179.91. Now isotherms go like this. 179.91 degrees Celsius. That's your isotherm. Well, we found out a lot of stuff about your state one. This is state one. Put a 1 on. There you go, there's state one. But what about state two? Now let's read the problem again. It says here, the temperature is lowered 20 degrees. They want the new quality and specific volume. New quality and specific volume. You're going to lower the temperature 20 degrees. Well, I can tell you what the new temperature is going to be. You can subtract 20. I can do that in my head. It's 159.91 degrees Celsius, isn't it? But they said it is at constant pressure, right? Let me read it. Constant pressure. The new temperature, we know the new temperature. What is the new quality and specific volume? Well, we can get it. The thing is, 159.91, that's colder. Here, let me kind of fake it here. $159.91 is here. This is the 159.91. It's colder, but they said it's constant pressure process. Now, it looks to me, if you're going to go constant pressure from 1, you're going to have to go from here to here. Here's state 2 right here. There's state 2. Okay. You understand it? That's constant pressure, but you see the volume got smaller. Here, let's draw that. Now we didn't add any weight. We didn't take any weight off. The pressure is the same. See, the pressure is determined by the atmospheric pressure and the weight of the piston. The piston didn't change its weight any. The atmospheric pressure didn't change any. That's it. But here's the difference. I probably should put that quite a bit down here. Yeah, this is really more like it. We're all liquid now. Let me get my blue color here. Can you see that we're in the compressed liquid region and we have all liquid? See here, we had a little liquid. Yeah, there was some liquid. We'll color some liquid things here. And then you had a lot of water vapor, some steam in here like that. And then what we did was we cooled it off, right? We lowered the temperature. We had a heat transfer out. We plunged this thing maybe into a bucket of ice, okay? That'll cool it off. That'll cool it off. And as it cools off, the piston comes down, the volume gets smaller, and it condenses until you reach a place where it's all liquid, and there's state 2. We're done. We did state 2. Now let's answer their question. They wanted the quality. Well, there is no quality at state 2. That's a trick question. Quality only exists inside the vapor dome. You can have it 0 here on the left, 100% on the right, but there's no quality outside the vapor dome.
How would you word a situation like that, like on an exam? Is it just undefined?
Undefined. Quality is undefined. Quality is undefined, but we can get the specific volume. Now to get the specific volume, see if you're in here, this is the saturated mixture region, and you use the saturated mixture table. I call it the vapor dump table. If you're out here in the superheated vapor region, you use the superheated vapor table. In here, this is called the compressed liquid region. Guess which table you'll use if you're in the compressed liquid region. What do you think? What table should we use? Let me
That'd
go
be-
to one of my, go ahead.
I was going to say compressed liquid table.
That's it. Yay, that's exactly it. Now let's go and find it. Now help me find it here. There's a compressed liquid table here someplace. Good going. And compressed, yeah, I found it. Several pages of it. It's table B.1.4. I need some room here. I need some room, so we'll just make some room. Here we go. I'm on table B.1.4. They call it the compressed liquid table. Ta-da, and that's what we want. Okay. Now, what do we know? Well, we know the pressure is, at state 2 is 1,000 kilopascals, because they say you have constant pressure. Read the problem, constant pressure. If you start off with 1,000 and you have constant pressure, well, you still have 1,000. Now we know the temperature at 2. It's 159.91 degrees Celsius. And they want us to find the specific volume. Okay, well, we need 1,000 table. Let me find that. There it is. No, that's 10,000. Just a minute. Dang it, they don't have 1,000 table. The bombs, they have a 2,000, but that doesn't help us. We need 1,000. But we can do this. I just need some room here someplace. See, that's what we had at 1. Let me move that down here where I can find it if I need it. I don't know if I need it. All right, now I got a little room to work here. We know we're at 1,000, but they don't have 1,000. They have 500, they have 2,000. But we do know the temperature. Temperature is 159. Okay. I'm having a little trouble here. We know the temperature is 159. I'm having some trouble here. I wonder what I'm doing wrong here. There is no quality because we think we're in the compressed liquid region. We're trying to find the specific volume. We lowered the temperature 20 degrees. But I'm having major problems here. They have an incomplete table here for some reason, and I don't know why. It's closer to 2,000 than 500. The temperature is 160. I tell you what, these isotherms basically go straight up. Whatever the specific volume is at 2, right here, well, that's at 2, but it's equal to VF at, why don't we just call it 160 degrees? It's dang close to 160 degrees. If you, what I'm going to use is I'm going to use the saturated table, the vapor dome table, and I'm going to go back to find 160 degrees. We're going to have to go to table B. Does that show up? Yeah, that shows up. Go to table B dot 1.1. And at 160 degrees Celsius, VF is equal to 0.00102. See it? And that's right there. Now we don't want it right there, we want it right here, but it goes straight up. So the specific volume at state 2 is, I would say it's dang close to the same thing. I would give an answer of V2 is equal to the 0.001102. Now let me see if I can convince you of that. Go back to the compressed liquid table a minute. I lost it there. And they do have at 2,000. See, here's where 2,000 is. There's 1,000. At 2,000 kilopascals and 160 Celsius, they do have that in the table. Let me write that for you. I don't know what to call it. Maybe call it V3. How's that? We'll call this state 3. At that state, it's 0.001101 cubic meters per kilogram. Now that's at 2,000 kilopascals. Now remember, when it was at 1,000 kilopascals, it was 0.001102. At 2,000 kilopascals, it's 0.001101. Hey, it didn't compress much, did it? What is that? 1/1,000,000th of a cubic meter per kilogram? Isn't that what it is? Look at these numbers. Look at that number, look at this number. Water doesn't compress much, does it? So maybe that's why they didn't bother completing that table because it just doesn't change much. The answer is, Mohammed, the answer is your specific volume at 1,000 kilopascals and 159.91 Celsius is 0.001102. Ta-da! It was kind of hard. We kind of got stuck, but we figured it out. Any comments or questions on that one? Well, we're going to work some more. If you're happy, I'm happy. Let's work some more. Here's your chance. I'm going to erase this, and we're going to do another one now.
And do you use that volume that you just found, the 0.001102, in the equation for the quality, or did you already determine that?
Well,
I'm a little bit confused why that's undefined, like you said.
tell me your name.
This is Nathan.
Nathan, you do not use that equation because we're not in the vapor dome. Quality is something that exists inside the vapor dome. We are not in the vapor dome. See, if you're out here in superheated vapor, you don't use that equation in the superheated vapor region because you're not in the saturated mixture. Do you understand? Let me write it.
Yes.
Quality is something that's inside the vapor dome. If you're outside the vapor dome, you can't use it. Now, you can use the superheated vapor table if you're over here, or you can try to use the compressed liquid table like I tried to do over here, but I couldn't find what I was looking for. What I wound up doing, Nathan, is I used the vapor dome table, but I knew that here, these isotherms go pretty much straight up. Now, there's a teeny tiny tilt to them, because remember how I erased it. This number was a 1 there. It tilts to the left, just can't even tell. Basically, water is incompressible, but quality is only for inside the vapor dome. Anybody else? Okay, well, we're going to do another problem. Mohammed, are you okay?
Yes, sir. I'm okay. Thank you so much for helping me out.
You're so very welcome. But that was kind of tricky.
Yeah, because I spent like an hour on this problem yesterday, and I was like, I'm not getting it how to do this problem. I was confused. And it's like, I don't know which table to look in order to get the answer for that specific one.
Mohammed, do not change your major.
Oh, no, sir. No, not at all. Not at all.
Do not, that goes for all of you. Do not
Yeah,
change your
I'm firm on
major.
it. Yeah, I'm firm on my major, for sure.
Oh, good. We'll figure it out. Okay, now we're going to do 233. Now let me find that. We're just doing PV diagrams today, and we're learning about them. Now this is water again at 400 kilopascals, quality of 75%. Well, let's draw that. Here's the PV diagram. And you know, it looks kind of like that. It's water. Now we want 400 kilopascals. Well, that's way down low. See, way up here, it's 22 megapascals. Holy cow, 400, that's way down here someplace. 400 kilopascal. And so we know we're on this 400. We know we're on that line there someplace. Ah, the quality is 75%. Now here's state one right here. Ta-da, there we are. It has a pressure. We're going to raise the pressure in a constant volume process. We're going to raise the pressure 200 kilopascals. You know what? We're going to go up to 600 kilopascals. Now, I've already done this problem. And I happen to know that if you raise it to 600, you bust out of the vapor dome and state 2 is here. But you wouldn't know that until after you look stuff up in the tables. But here, we'll show you. All right, now first thing we're going to do is we're going to get our quality. Now, the specific volume at 1 is going to be VF. Help me find it. Go to 400 kilopascals. And I found it there. And it's 0.001084 plus, they said it was 75%, right? Times 0.46138. We're going to get our quality at state 1. Okay, go for it. I want you to do it. And then I'm going to ask you, I'm going to ask somebody and see if they got the right number. Because I got to find out if you guys are listening to me. All right, I think I know what the quality is at state, not the quality, the quality, not the quality. What am I trying to find anyway? I just had a senior moment. We're raising the pressure, and the new pressure is going to be 600. Okay. All right, I did that, and I got the specific volume at state 1. Now let me see. Let me pick on somebody here. There we go. How about my friend? Well, I was just talking to Nathan. Nathan, what'd you get for this quality? It's or not quality. The specific volume at state 1.
0.347119.
That's what I got. Those are cubic meters per kilogram. We're doing great. Okay. Now we're going to get the specific volume at state 2. Now, if you read the problem, it says we're doing 233. If you wondered, well, what's he doing now? Well, he's doing 233. Constant volume process. See, the volume staying the same. This specific volume was 0.347119. And now it's still the same because it's constant volume. So we know what it is. It's 0.347119. Yay, good deal. What else do we know? Well, that's the specific volume. We also know the pressure. It's 600 kilopascals. Hey, why don't we do the device sketch, and then we'll answer their question. What do they want to know? I forget. Let me read this. Constant. They want to know the temperature. That's what they want to know. Well, we'll find it. And first of all, what was the temperature at 1? Let me find that. I'm just curious. The temperature at 1 was, got lost here. 400. It's 143.63, isn't it? 143.63. This temperature right here a little bit rugged there.
What table are you looking at again?
Thank you for asking. It's the table that's going to have 400 kilopascals on it.
Yeah, I've been trying to find that.
It's table B.1.2.
Okay.
Go to B.1.2, find 400 kilopascals, and it says the temperature is 143.63. This temperature is 143.63 degrees Celsius. And of course, the temperature here is 143.63, and the temperature down here is 143.63 degrees Celsius. It's an isotherm. But they want to know the temperature at state 2. Well, see, at state 2, at state 2, this will be T2. I don't know what it is, but we're going to find out. It's going to be hotter. Now let's draw our device sketches to see what's going on here. I need some room here. Is there a room to put a piston cylinder right here? Yeah, there's room. Okay. Now, this is 75% vapor. So you know what that means? There's just a little water down here in the bottom, and it's mostly vapor, huh? But it's got a little water, some water drops down there. Okay. That's state 1. Now, here comes state 2. I need some room there. Here comes state 2. I think it's all vapor there, and nothing changed on the volume. It didn't get bigger. It's constant volume. They have a fancy name for that. They call it isochoric. Constant volume. There isn't any liquid anymore. They made it hotter, guys. See, T2 is going to be hotter. We're going to find it in a minute. T1, does that show up on? Yeah, T1 is 143.63 Celsius, but T2 is hotter. You know what they did? They put it on the stove. I don't know how they kept the piston locked. They must have put some glue or put some super glue on that piston and put it on the stove, and you'll have a heat transfer in. And you know what? That water evaporated, didn't it? But the pressure went up. Can you see that pressure went up? Well, I need to draw that. The volume didn't change, but the pressure changes. It's like somebody put a heavy weight on there. They put some heat in there, or they transferred some heat energy. And the thing is, if they didn't put that weight on there, then the piston would go up. Do you understand? It would expand. But as they put it on the stove, they started adding weight to it, a little bit by little bit, little bit by little bit, until the pressure came up to 600 kPa. and we're going to find the temperature. Is that what they want? Let me read it. 233. What is the new state? They want the quality. There isn't going to be any quality, and I'll tell you why. If you go to 600 kilopascals on table B.1.2, you'll find VG on table B.1.2. VG is 0.31567. You really need to find that. But see, we know we have a specific volume bigger than that. See, this is 0.31 something. You know what that is? That's the specific volume right here. That 0.31567. That's VG. That's the specific volume right there. But we're not there. We're here. We're at 600, all right. See,
Mr. Griffin?
Yeah, I'm listening.
So it's 600 kilopascals, right? Like this isn't
Right.
temperature? Okay, so I found the numbers that you're talking about, but it's to
Uh-huh.
like 600 Celsius, not 600 kilopascals. At least with the numbers I found, it says the pressure is like
Can
158.
you look on table B.1.2 for me and find
Yeah, that's what
600 kilopascals? Can you find the 600 kilopascals?
No, but the numbers
Well,
that
I
I
can. Look, who am I talking to?
Alex,
Alex, are you on table B.1.2?
yes.
Go down till you find 600 kilopascals. Can you find it?
Okay.
Now go over here till you can find VG and tell me what it says for VG.
It says for VG 0.001101.
No, that's VF. I want
Oh,
VG.
sorry, 0.31567.
Yeah. Yeah, I wrote down the. Yeah, there it is. I wrote it down correctly.
Yeah,
It's
see, I know where those numbers are coming from, but if I follow it over, the 600 isn't pressure, it's temperature. And that's what was confusing me.
no, the temperature is 158.85.
Okay, well
The
those are
pressure
flipped.
is.
Those are flipped in the back of my book. Then it's showing that Celsius is
Oh,
600
good.
and
Yeah.
pressure.
Mine
Alex,
is actually the same way. Like it shows
thank you.
600 under Celsius.
So I know that was like hard. That was not easy to explain, but that was what the issue was. Is those two numbers
Alex
were
and the
flipped.
rest of you, they flipped those. They've got those wrong.
Okay,
That
so
makes a lot
the
of
book
sense.
is wrong.
The book is wrong.
Thank you. I was so confused this whole time.
Are you on the online book?
I'm so
Yes.
I'm so
The
glad.
physical
that you guys
copy has it
mentioned
correct.
that. I'm sorry. Say it again.
The physical copy of the book has it correct.
Yes,
think
the
it's a
physical
problem with the
copy
online
has
one.
it correct. That's right. But the digital copy has flipped that, and I forgot to tell you guys that.
Okay. That makes a lot more sense now.
Oh, okay, yeah. I should have told you guys that the digital book has turned those around. Whew, okay. And now what I was telling you is what we got is 0.347. That's bigger than 0.315. So we're out here in the superheated vapor. That's where we are right there. Now we're going to find the temperature. Now to do that, we need the superheated vapor table. And I think they got this right on the digital copy. Go to 600 kilopascals. Go to 600 kilopascals. This is table B.1.3. B.1.3. And we know what V2 is. It's 0.347119. Okay, we're going to find it now. Well, I tell you what, it's between a temperature of 158.85 and 200 degrees Celsius, and the specific volume is 0.31567 and 0.35202. But see, what we want is 0.347119. Now, this is all at 600 kilopascals on table B.1.3. Can you find these numbers on B.1.3? Can you find them? And I'm waiting. I want to hear several uh-huhs.
I can, except for the 158. That was on the last table.
Well, they have it in quotes there. Tell me your name. Is this Nathan?
I'm sorry. I'll get in the habit of that. Nathan, this is Nathan.
Nathan, it's 158.85 when it's saturated, when it's on the saturated vapor line. And the specific volume is 0.31567. But when it's 200, it's 0.35202. You understand?
Yeah, I understand what you're saying. I don't know why it's not on the table, but
Well, they have the first line there is the saturated. That's when it's on this saturated vapor line, Nathan. And the temperature at 600 kilopascals when it's saturated is 158.85 degrees Celsius. It says saturated way over on the left.
yes,
See it?
okay. Yes.
Now what we want, T2 is going to be right here. Do you notice this number is between those numbers? T2 will be between those numbers. We have to interpolate. We're going to find T. See, I drew T2 for you. Here it is. But we don't know what it is. So I'm going to shut up for 2 minutes, and you're going to interpolate this and get T2 for me. Go ahead. Let's see if you can do it. Well, I did that. And I'm getting a T2 of 194.45 degrees Celsius. See that T2? It's 194.5 degrees Celsius. Comes up here like that. But I'll wait a minute or two and see if anybody can get that.
I got this.
I'll write it out if you want me to.
Yes, I got that one too.
Hey, did you get that?
Yes.
Good. Well, there's 2 of us. Wonderful.
Could you maybe write that out?
I'll be glad to. Okay, I'm gonna write this out. And just, my problem is having some room to write. I'll sacrifice these device sketches, but see, device sketches are important. This is what's happening. There's a heat transfer in, the volume stays the same, but the pressure goes up and the temperature goes up. The temperature goes up to 194. It's an isochoric process, but I needed the room, so we'll sacrifice our device sketch. And here's what you do. You take 0.347119 and you subtract 31567 and you divide by 0.35202 minus 0.31567. Somebody called my phone. They probably want money. I'm not going to answer it. Okay, and then what you do is you multiply by 200 minus oh gee, I'm running out of room here. Does that show up okay? Yeah, that shows up okay. But now you're not quite done yet. You have to add all that to the 158, running out of room here, 58, 85. Does that show up on, yeah, barely. Yeah, it shows up. Now, if you'll do all of this, if you do all of this, that's what I did, and you'll get 194.45. Who was that asked me that?
That was Alex. And that makes sense. Yeah.
That's what you do. Okay, well, that was a lot of fun. Let's do another one. We got 10 minutes.
Hey,
If we don't
Professor,
have time, go ahead.
I have a question. Is the exams gonna be posted on Blackboard?
Yes, they are going to be on Blackboard.
Like how many hours are you gonna give us to work on it?
I'm going to give you, I think, 3 days.
Oh, okay, that sounds good.
So you won't have any. Time is not, who am I talking to?
You talking to Reagan?
Reagan. Thank you for asking, Reagan. Time is not a problem. You'll be fine. Let's do another problem. Now, I don't, can I erase this, or is there any other question? Well, if there's no other question, I'm going to erase it. Say goodbye to problem 233. And I'm going to discuss problem 258. Now, I don't have time to go through the whole problem with you. I wish I did. I would love to. But we have time to get started and to show you the important things. Probably the most important thing is the PV diagram. So let me show you what that would look like. Now, what is this substance? What is this 258? Let me find it here. I'm shopping around now, trying to find 258. I found it. It's ammonia. Ooh, it's ammonia. So don't use the water table. But see, ammonia has a graph like that. Now, next time, what's today, Thursday? Next Tuesday, we need to do some ideal gas processes. See, that's what I want to do with you on Tuesday, next Tuesday. When you do ideal gas processes, you don't have a vapor dome. What you have is a bunch of isotherms that kind of go like this. See, these isotherms here are kind of goofy. They have a really strange shape. They come up here like this. Then they come over here like this. And they go up here like that, pretty essentially straight up. And then a hotter one comes up here like this, comes over here like this, goes straight up. And we could draw some more. I tried to explain why that is the other day. But we're going to study PV diagrams with ideal gases on Tuesday. But right now we're looking at 258, and I've got about 7 minutes to try to show you what the process would look like. Trying to find the problem now. This is 258. I found it. It's ammonia. It's in a piston cylinder at 700 kilopascals and 80 Celsius. Okay, well, go to ammonia. Go digging back here in the tables and find ammonia. We got to find where we are, see? Ammonia, let's see. Aha. And which table do we always go to first? The saturated table, what I call the vapor dome table. So go to the vapor dome table for ammonia. And what we need is 80 Celsius. Now that's table B.2. And 80 Celsius is kind of 2/3 of the way down the page. So that means it's about 2/3 of the way up the PV diagram. It's just opposite. So here's your 80 Celsius isotherm, and the pressure right here, the saturation pressure is 4140.5, 4140.5 kilopascals. We could even write the VF, that little VF thing. We could write it down. It's 0.001978. And we could write this one down here too. That's the VG. That one is 0.02951. Okay, well, we've located that. Now, what did they say about it? They said we're at 700 kilopascals. 80C. Well, 700 kilopascals, that's a lot smaller than 4,140 kilopascals. It's down here someplace. 700 kilopascals is down here someplace. So you know what that means? That means that, bingo, we're out there in the superheated vapor region, aren't we? See this 80 degrees Celsius line? It comes through here. There's your 80 degrees Celsius. And here's your 700 kilopascals. So if you wanted the specific volume, it's state 1. That's state 1. Oh gosh, we're running out of time. We got 4 minutes. You'd have to go to the superheated vapor region. Do they have 700 kilopascals for ammonia back there? Dig around with me. Superheated vapor ammonia. Oh, it's sad. They don't have 700. They have 500. They have 600. They have 800. But we could get it because they have 600 and 800. It'd just be halfway between. We could get that. But now, I don't have time to show it to you right now, but they're going to cool it at constant pressure to saturated vapor. All right. Well, here, let me kind of fake this a little bit for you. Oh, come on. We're going to cool it at constant pressure. Now, how do you do that? Hey, here's how you do it. At constant pressure, we're going to go from state 1, and state 2 is going to be right there. See it? There's state 2. Constant pressure. We're going to cool it. Take your piston. Do I have time to draw a piston here? Oh gosh, we have 3 minutes. Yeah, I got time. Okay, you're out here now, and we're going to, at constant pressure. Don't put any more weight on it. But see, the volume decreases. And the reason why it decreases is we plunge this thing into a bucket of ice water. See, that'll cool it off. Volume goes down, and it'll just start to condense. You'll start to get some little drops of liquid ammonia, and you'll get a puddle there. You'll start getting a puddle too. Then what? Keep reading. The cooling continues to -10. Well, see, it was at 80 degrees. The cooling continues. Oh, they're going to lock the piston with a pin. So here's state 2. Here's state 1. And here comes state 3. We lock that piston with a pin. It doesn't get any smaller or any bigger. But we're going to get colder. Put it in a bucket of dry ice. That'll do the trick. And you'll have more heat transfer out. And the temperature is going to be, what is it, -10? Now, you know what I think? I think it's going to do this. It's going to be an isochore. And state 3 is going to be down here. And the temperature will be -10 degrees Celsius. So this is a 2-part process. We're going to have an isochore going from 1 to 2, but from 2 to 3, it's going to be a, I said that wrong. From 1 to 2, it's an isobar, constant pressure, and from 2 to 3, it's an isochore. Your PV diagram has 2 processes on it. It's sad, but our time together has come to an end. If I had more time, we'd go through that problem in detail, but we don't have any more time. Here's your last chance to say anything. Go ahead.
Can I ask you a quick question?
Sure.
We can resubmit our homework problems if we wanted to redo them? Is that correct?
Well, you're welcome to redo them, but did I give you a grade?
Well, I'm talking about
The grade?
the one that's due this Friday. They're not due yet.
Okay. Well, you don't need to resubmit it if it's not due. I don't understand your question.
If I already submitted the problem, but I want to rework it and do it correctly, can I do that?
No, don't. Don't make me work any harder than I have to, please. Who am I talking to?
Nathan, I'm not trying to make you work harder. I just realized I did it. I just realized I did it wrong, and so I wanted to resubmit it.
Nathan, the
Yeah.
chances are you're going to get a 3 out of 4 if it's wrong. But you've worked hard on it. In this case, you've turned it in, and the grade is going to stick. It's sort of like you turned it in. I graded it.
That's fine. That's fine.
Look
That's
at your
fine.
grade, Nathan. What did I give you?
It's not due till Friday. I don't think you've graded it yet. It's fine. Don't worry about it.
Well, just a minute. I've graded some papers. What's your last name?
It was the one that you did. It was problem chapter 2, problem 36.
Okay. Well, I don't see it here. Maybe I haven't graded those yet, but if it's turned in, you're going to get
It's-
whatever you turned in.
That's fine. Thank you. Okay.
Yeah, I wish I could help you more, but I'm doing the best I can, Nathan. Anybody else? Last call for any comment, because I'm going to sign off.
Thank you.
Thank
Have a
you,
good day,
guys.
Mr. Griffin.
Good day.
Bye.
Be good.
Okay.
I'll see you later. Bye.
See ya. Bye.